from the Saints Academy in Beverly. Over the past 9 years, our school has helped collect plant growth data for the marsh located at Canoma Point in Essex. Canoma Point Marsh has 5 transects in 5 different areas of the marsh. As you can see, our marsh is filled with a variety of plants, animals, and insects and appears to be thriving. However, upon a closer inspection, you will notice evidence of marsh fragmentation and signs of stress which are not confined to just one area of the marsh. In 2020, we started to be concerned about the trend in data, that is, the loss of plants and changes in the salinity levels. 3 years ago, we began a database for the nitrate and nitrite levels in the water because we wanted to see if there was a correlation between high levels of these compounds and the plant loss leading to marsh fragmentation. The correlation was accurate. However, this year, instead of the high nitrate levels that we expected, the levels were lower, while the salinity levels were higher and the plants were affected in a different way. Why was this happening?
After reading a study by Nathaniel Weston of Villanova University, who addressed the impact of climate change on a marsh's survival, we analyzed our data to see if climate change was responsible for the fragmentation we observed in the marsh. To quote from Mr. Weston's summary, "In the South, the Great Marsh is losing the battle of climate change, but although struggling for now, the Northeast is keeping pace with sea level rise caused by climate change."
We hypothesized that if climate change is the major reason for marsh loss and fragmentation, then we should see the impact in 3 ways. First, the flood level of the marsh should be rising each year. Residents in the area have stated that during high tide, the water overflows onto the roads and spills up to the property lines. During low tide, the ground should be increasingly soggy, similar to a sponge that cannot soak up more water. Plants cannot survive underwater.
Second, salinity levels will increase because more salt will be deposited with each high tide. Salinity tests at transects 3 and 4, which are closest to the ocean, have readings as high as 45 to 50 parts per thousand, which is affecting the types of grasses in those transects.
Third, a drier summer will impact the production of nitrates in a positive way. Elevated levels of nitrates lead to excessive algae blooms that impede the production of oxygen in the water through photosynthesis, resulting in the death of plants and fish. Last year, Transect 2 was affected the most with massive amounts of algae and dead fish. We believe that the drier summer of this year produced less nitrate in the water and therefore less algae.
Our study continues to monitor areas of stress using GPS data while analyzing groundwater, salinity, and nitrate concentrations. Even though the marsh is struggling with the effects of climate change, the data collected may help us understand the factors influencing the survival of our marsh.
This is a map of the marsh at Canoma Point. The map shows the locations of 5 transects. Transects 0, 1, and 2 are farther away from the ocean and depend more on tidal water or groundwater. Transects 3 and 4 are closer to the ocean. We analyzed 45 groundwater samples for nitrate and nitrite levels. The samples were taken from 3 sets of wells located along a 25-meter transect line in 5 different locations along the marsh. A set consists of a shallow, a medium, and a deep well, and are evenly spaced along the transect line. We completed a chemical analysis of the groundwater at the wells where salinity tests were conducted and documented the dead areas of the marsh using an app called Gaia Earth.
To test the nitrate and nitrite levels in the groundwater, we used the API nitrite and nitrate saltwater test kits and compared the results to the color key provided. An acceptable range of nitrates should be less than 10 parts per million. Therefore, water that has the proper balance of nitrates should turn yellow. If nitrates are essential for plant growth, then an elevated level will adversely affect the plants, resulting in fragmentation of the marsh.
Transect 0. Transect 0 extends up from Canoma Point Road. Accessing the site requires a walk through a muddy, dense growth of Phragmites, which then opens out to a field of spike grass, marsh hay, glasswort, and cordgrass. The GPS map shows the additional areas of stress, and also an increase in the size of areas experiencing stress. Stress was determined by observing areas of excessive ponding depressions with algae, as well as visible signs of fragmentation. In 2022, the map overlapped itself, which is still seen in 2023 and 2024 with the red arrow.
2 years ago, Transect 0 was completely dry. Now the ground is soggy in many areas around the Transect line. The small pools of water began forming last year, have increased in size, and are lightly coated with algae. A channel of tidal water, splitting the Transect in two, creates another section to the Transect. This area was a small sinkhole last year, but is now filling with water. It was about 28 centimeters deep, meaning halfway up your boots. We suspect that the flooding and lake problems seen in Transect 2 are spreading towards Transect 0 and 1 because they are in close proximity. If the trend continues, it is possible that the back portion of Transect 0 will also become a lake with severe fragmentation and loss of marsh.
We think this could happen because in 2017, Transect 2 was also completely dry and fed by tidal water. If you look closely, you will see an indentation in the marsh depth. The following year, that began to develop in the water. By 2023, there were extensive algae plumes and extreme ponding, causing visible loss of plants and land. Before continuing, we need to explain how to read our plant growth charts. Salinity information is shown under the graph. Numbers written in red represent a super high level of salt. Black is high and blue is medium. The color key for plants is to the right of the graph. We noticed a change in the plant growth from 2023 and drew a correlation between the higher levels of salinity to the growth and spread of the grasses. We concluded that because the summer of 2024 was dry, the marsh grasses depended more on tidal water. The saltier tidal water caused a change in plant growth.
For example, in areas of high salinity, Phragmites, shown in green and yellow, marsh hay, shown in light brown, and spikegrass, shown in blue, are thriving, as well as cordgrass, shown as a peach color, and glasswort, shown as a dark brown. Glasswort is a pioneer plant and can grow on various levels of salinity. As previously stated, an acceptable nitrate range is bright yellow at 5 parts per million to golden yellow at 10 parts per million. 6 out of 8 tests were in the acceptable range. However, 2 out of 8 tests presented elevated levels of nitrate. The deep wells at Site 1 and Site 3 were a shade darker. Algae is scattered in the water that is ponding. This is important because excessive amounts of nitrate produce algae blooms, which stop the sunlight from penetrating the surface of the water. Aquatic plants cannot perform photosynthesis, resulting in reduced levels of oxygen in the water. Aquatic life must compete for the limited amount of oxygen available.
Nitrite is an inorganic compound consisting of 1 nitrogen atom and 2 oxygen atoms. In this form, nitrite can be toxic to plants. However, under the optimum conditions, nitrite can be converted into nitrate, plant food. Acceptable levels of nitrite are 0 to 0.24 parts per million. 8 out of 8 tests were in the acceptable range. Samples that appear more green or teal in color indicate a nitrate is also in the sample. The transition zone and the area in Phragmites were bright teal, signifying higher levels of nitrate mixed in. If the water in these wells undergo a chemical change and become nitrate, we may also see fragmentation beginning at these sites due to higher levels of nitrate in the water.
Transect 1. Transect 1 is along the Canoma Point Road in the same area as Transect 0, but to the right and more along the road. There are a variety of plants and they appear to be thriving.
However, we also observe signs of stress. The ponding that started last year has increased in size, stretching out towards Transect 0 and 2. Here, the water is knee-deep and patches of algae float on the surface.
The GPS map indicates that the areas under stress have increased significantly in size. In 2022, the area shown in red is now a small part of 2024.
On this plant chart, the first thing you notice is the red. Red indicates a flooded area where grasses processing Phragmites are either scarce or gone. In 2020, the placement of the transect line was changed because the record coordinates was unavailable and had to be estimated. However, the ponding observed is located along the previous line. The salinity samples taken from the wells in the Phragmites were exceptionally high, yet the Phragmites are still present starting at meter 3. Does the fact that the core grass is thriving suggest that it is trying to restore balance at the site? If so, the roots will stabilize the soil and prevent fragmentation.
Although Transect 1 had both water and algae present, all the nitrate water samples shown in yellow were in the acceptable range of 5 parts per million. 7 of 9 nitrite samples were in the acceptable range of 0 to 0.24 parts per million. However, 2 of 9 samples yielded a bright teal color, indicating the sample contained a small level of nitrate. Given these results, Site 1 shallow and Site 3 medium should be monitored. The concern is that if nitrite covers nitrate, algae will continue to spread.
Transect 2. Transect 2 is almost completely flooded. Ponding here is so large it looks like a lake. However, Phragmites have regrown and are in the same meter range as in 2021, probably due to their dense root system. All other plants are gone. There is not enough land to support the cordgrass that could exist in high levels of salinity. The salinity at Transect 2 registered at the super high level, except for the area where the Phragmites have reappeared. Those wells registered in the mid to low end of the high salinity scale. This may be another indicator that the Phragmites are acclimating to slightly elevated levels of salinity.
The GPS data maps for 2021 and 2023 resemble each other. However, 2023 is now bigger in size. Collecting data in Transect 2 using the GPS app was challenging because the grass around the perimeter was difficult to walk on due to its instability and fragmentation. In certain areas, the waist-deep water made it impossible to continue walking. 8 out of the 9 nitrite samples at Transect 2 were in the acceptable range. However, the Site 3 deep well indicated excessively high nitrate levels, 5 parts per million compared to the acceptable range of 0.24 parts per million. Raises a concern because elevated levels of nitrite are toxic to most marsh plants. In contrast, Phragmites require more nitrogen. This information is based on a study conducted by the British Ecological Society in 2004.
Transect 3. Transect 3 is located at the end of Canoma Point Road in a more residential area and is close to the road. Over the past 7 years, the area around the Transect line has experienced severe stress as seen by excessive rack and mud. Last year, the same area of marsh was in full bloom with glasswort and marsh hay. But this year, there was significantly less marsh hay and spike grass was not found. Cord grass was thriving in the super high salinity levels of 38 to 50 parts per thousand.
Without rain, high tide is the only source of water for plants. We researched the average salinity levels of the Atlantic Ocean are found to be 35 to 38 parts per thousand. This transect has an excessive amount of salt, which explains why no other plants are growing and why Phragmites are experiencing dieback, slowly moving away from the high salt concentrations. We think that the high salinity levels are caused by salt deposits accumulating in layers at each high tide. If the summer had been rainier, the rainfall would have diluted the concentration of salt.
The nitrite test results were all 5 parts per million, which is the acceptable range. 7 out of 9 nitrite samples were aquamarine in color. 2 out of 9 were teal, meaning the possibility of nitrite converting into nitrate is low. The GPS map outlines an additional area of stress. You might expect the land at Transect 3 to be flat because it eventually extends out to the ocean. However, there are many low patches and ditches. The rectangle indicates the position of a large hole filled with mud. Around the hole was rack and dead marsh hay. We called this area the Green Crab Graveyard. Although we didn't count the crabs, there were probably over 40 of them. Why were there so many dead crabs?
An article in Science Direct stated that green crabs survive in salinities ranging from very low to very high, with some studies reporting survival in salinities below 5 parts per thousand, and above 50 parts per thousand. Furthermore, according to NOAA, the National Oceanic and Atmospheric Administration, green crabs can survive excessive flooding from climate change because they can tolerate a wide range of water temperatures and salinity. What then could possibly be killing them? We agree with a study reported by CNN stating that extreme water temperature swings cause the metabolism of crabs to speed up to the point where the crab cannot eat enough food to maintain homeostasis. In a 24-hour period, the temperature fluctuated from a low of 52 degrees to 61 degrees Fahrenheit. Live crabs were found under the sand to keep warm. Crabs that were stuck in the marsh hay did not survive.
Transect 4. Transect 4 and Transect 3 are parallel to each other and are about 10 feet apart. Transect 4 is closer to the ocean, while Transect 3 is closer to the road. The entrance to the transect is muddy and spongy. It was easy to create a puddle while walking and get stuck in the mud. Similar to Transect 3, the land has low patches and ditches filled with murky water and algae. The GPS map indicates additional stress areas which were referred to as low patches and ditches.
Even though Transect 4 is just a few meters from Transect 3, the plant growth is different. Transect 3 had predominantly cordgrass and glasswort with only 4 meters of Phragmites. Transect 4 is the opposite. The plants that thrive in lower salinity levels are present. Phragmites, marsh hay, spikegrass, and glasswort with very little cordgrass. Even though marsh hay will grow in areas with salinity levels between 19 to 35, our readings were at the higher end of the polyhalion scale. This surprised us. Could this be another example of the marsh adapting to newer conditions?
In Transect 4, 8 out of 9 nitrate test samples were in the acceptable range at 5 parts per million. The deep well at Site 2, transition zone, was also acceptable, but presented the teal color. The possibility of nitrite converting to nitrate is again low. Conclusion. At the beginning of our presentation, we asked the question, is the marsh at Canoma Point adapting to climate change? Without soil samples showing the layers of soil deposition, we can't say for sure. We don't know if sediment deposition is helping raise the height of the marsh, thereby helping to control the flooding. We do believe that the marsh at Canoma Point is still showing signs of stress, that no single factor is responsible for the current condition of the marsh. There are many components interacting together. Climate change, levels of nitrate, and salinity levels.
We have data that supports the claim that some parts of the marsh are trying to adapt to climate stress. Salt-tolerant plants such as cordgrass have increased in every transect except for Transect 2. But even Transect 2 is fighting back with less algae due to lower levels of nitrate in the water. With less algae, there's more oxygen available for the fish and plants. Since plants stabilize the sediment, fragmentation and marsh loss may slow down. In addition, the salinity data suggests that Phragmites are becoming more tolerant to elevated levels of salt. Even though Phragmites are invasive, they are exceptional carbon filterers and actually help clean the air. However, there is still a concern about the areas that are not absorbing excess water. These areas risk flooding, which could add to the problem of marsh loss.
If climate change is truly the reason for marsh loss and fragmentation, then changes in nitrate and salinity levels, which ultimately impact the type of grasses present, should be continuously monitored with these variables in mind. It is our opinion that the marsh at Canoma Point is trying to deal with climate stress one small step at a time. Thank you for your attention. Are there any questions at this time?
If you have questions, raise your hand and shout them out, and we'll repeat them, and the folks up here will answer them.
Why do you think there's less
there's less nitrate this year compared to last year?
The reason that it's causing low nitrate this year is one reason of this can be the lack of rain. Nitrogen in the air makes its way into the ground through rain and lightning storms, and since we haven't had a lot of storms this summer, that may be the reason why there is low nitrate.
Are there any other questions at this time?